our entire concept of trigonometry so far has been totally based on the right triangle. And that has allowed us to solve some interesting problems, but at the end of the day, right triangles are limited because the types of angles that live inside them are acute. They have to be between 0 degrees and 90 degrees. But the whole goal of trigonometry is to solve problems when angles are involved. And there are way more angles out there than the angles between 0 degrees and 90 degrees. What if we had to deal with a situation with a 120-degree angle? Well, our current concept of trigonometry doesn't help address that. So in this video and the next one, what we're going to do is build a bridge between our current concept of trigonometry based on right triangles to a new concept of trigonometry based on circles, because a circle has 360 degrees of rotation inside it. And so naturally, it's a better sort of mathematical playground where we can set up trigonometry. And the good news is all of the trigonometry that we get from the circle is going to tell us everything that we get from the trigonometry here, but also way more. So the point is, it's really worth building that bridge and moving to this new geometric arena, if you will. Now, before we do that, we need to think about what exactly is a circle, because that's going to come in handy when defining an entire mathematical system based on circles. So what is a circle? Well, every circle has a reference point called the center of the circle. So the center of this circle is probably somewhere around there. It's not actually a part of the circle. But based on that center, a circle is all the points that are the same distance away from the center. So if I pick any point on the circle, like that point, and I think about how far is this point from the center of the circle, no matter which point I picked, I would get the same answer, and that is the radius of the circle. So that's what a circle is. It's given some fixed point, the center, it's all the points that are the same distance, the radius, away from that given point. Okay, the good thing is when we build our new concept of trigonometry, we can actually choose any circle we want to choose. And so we're going to make a very simple choice. We're going to choose a radius of 1. That's where the name unit circle comes from, because unit just means 1, and unit circle is just a fancy way of saying a circle of radius 1. So everything that we do going forward is going to be based on this circle, the unit circle of radius 1. Now, the other thing is we're going to want to refer to actual points on the circle, and in order to do that, we're going to need a coordinate system where we can sort of give the circle an equation and then talk about actual points on the circle. The good news is we can also choose how to draw our coordinate system. Drawing the coordinate system over here, for example, when discussing that circle is probably not the best idea, because the equation of that circle based on this coordinate system is sort of more complicated than it needs to be, right? Where would you draw a coordinate system if you wanted to talk about any point on this circle? Well, I think drawing a coordinate system that is based on this circle and where the center of the circle is the origin of that coordinate system is probably a good idea. So that's what we're going to do. So now let's zoom into the unit circle and coordinatize as desired. So now that we have a unit circle and a nice coordinate system, we can begin to talk about the points on the unit circle. So 4 of those points are easy to talk about. If you start at 0, 0 and move to the right one, you would get to 1, 0, meaning that is a point on the unit circle. And similarly, you can deduce that 0, -1, -1, 0, and 0, 1 must also be points on the unit circle. The question is, how do we talk about literally every other point on the unit circle? So if we just have x, y, what's the relationship that we know between x and y? Or in other words, what's an equation that we can write down such that the only points that make that equation true are the points on the unit circle? Well, we can use the definition of a circle, right? We can say we want the distance between x, y, and the center, 0, 0, to be 1. The only points that make this equation true are points on the unit circle. So this is an equation for the unit circle. How do we write this equation down purely mathematically? Well, we can use the distance equation, which tells us that the distance between any 2 points is the square root of the change in x squared plus the change in y squared. So if we apply that to this, we would get the distance between x, y, and 0, 0 is the square root of x minus 0 squared plus y minus 0 squared is equal to 1. Okay, we can clean this up a little bit because x minus 0 is just x, so this is the same as the square root of x squared plus y squared is equal to 1. And to eliminate the square root, we can just square both sides of this, and we would get x squared plus y squared is equal to 1 squared, which is just 1. And this gives us our final nice and simple equation for a unit circle, x squared plus y squared is equal to 1, which comes from the distance formula. But if you're wondering, well, why is it true other than the distance formula? Well, if you just think about this point xy, if we build a right triangle based on this, and automatically you can kind of see there's going to be a connection now, right, between right triangles and circles. But if we build a right triangle here, then what is that hypotenuse? Well, since we're in a unit circle, it's a radius, and so it's 1. And what is the length of this side of this triangle? Well, based on the fact that this is 0, 0, the length of this would just be the x coordinate of that point, so this would just be x. And the height of this triangle would just be the y coordinate of that point. That would just be y. And if you apply the Pythagorean theorem, you would get x squared plus y squared is equal to 1 squared, which is exactly what this equation is. So if you're wondering why the distance formula is true, ultimately it does go back to the Pythagorean theorem. With that being said, we are now ready to do what we wanted to do, which is build a new concept of angle using circles. So the first thing to discuss is that angles now correspond to rotations, okay? So if we're going to talk about rotations, we need a starting position for all of our rotations. And we can choose any position to be a starting position to rotate from, but the convention is to choose the positive x direction. So this right here, that is the 0 degree direction. It's arbitrary, but that is our choice, okay? That is 0 degrees. That's our starting position for all of our rotations. Now, when we rotate, there's 2 directions we can rotate, right? We can go counterclockwise and we can go clockwise. And the way that we're going to differentiate between those 2 directions is with a positive sign and a negative sign. So if we do a counterclockwise rotation, we're going to consider that positive. And if we do a clockwise rotation, we're going to consider that negative. And so let's think about what 30 degrees means in this system. So what does 30 degrees mean? Positive 30 degrees. Well, if we start at 0 degrees, positive means counterclockwise. So if we rotate, so maybe this looks about 30 degrees. So if this angle is 30 degrees, then we would end in this position right here. That would correspond to a 30 degree rotation. Okay. What about negative 30 degrees? What would negative 30 degrees look like? Well, negative just means clockwise. So if we start at the same starting position and go the other way, we would end in a situation that looks probably something like this. So this is negative 30 degrees. Now, it's important to realize that the physical angle here, that angle is still positive 30 degrees, but the angle that describes the rotation is negative 30 degrees, okay? And the angles that we're talking about are going to be describing rotations. And so for that reason, what are the possible rotation values we can possibly think about? Well, we can keep rotating around and around the circle infinitely in either direction, which means our new concept of theta is actually going to be anything between negative infinity and infinity is going to be okay. So any real number now, we can consider an angle and deal with based on this circle. Now, this should make you wonder, this angle that I said was 30 degrees. How do we actually know that it's 30 degrees? Aren't there other rotations that will leave you with this direction? So if you rotated, for example, 390 degrees, then you would have rotated 360 degrees and another 30 degrees, and you would still end up in that position. So this right here, this thing right here, we could call that the terminal side of the rotation, but knowing the terminal side of the rotation doesn't actually tell you the angle of rotation, because this terminal side can apply to 30 degrees, it could apply to 390 degrees, it could also apply to negative angles. So how could you get to 30 degrees, positive 30 degrees, rotating this way? Well, you would have to rotate 330 degrees this direction, and you would get to that same position. So negative 330 degrees is another angle that has a terminal side which is the same as 30 degrees and 390 degrees. One way of describing this is to say that 30 degrees, 390 degrees, and negative 330 degrees are what we call coterminal angles. Okay, so we've done a lot. So we've been very thoughtful about angles. And an additional way we can be thoughtful is, why are we doing everything in degrees? Why does a circle even have 360 degrees? It's sort of a random unit. If you think about distances, we're used to all sorts of units, like feet, inches, meters, kilometers, miles. How come for angles we only have degrees? The answer is we don't. There's actually another really good option. So let's begin to discuss radians. The main thing that you need to know is that there are 2 pi radians in a circle. And since we already know there are 360 degrees in a circle, it must be the case that 360 degrees is equal to 2 pi radians. Or in other words, 180 degrees is equal to pi radians. And that's the equation we're going to use to convert back and forth between radians and degrees. But before we do that, let's stop and acknowledge why degrees and radians are defined the way that they are. For example, why are there 360 degrees in a circle as opposed to a nicer number like 100? Well, the answer to that is, if we're thinking about some random fraction of a circle, like 1/18th of a circle, because the number 360 is evenly divisible by so many numbers like 18, 1/18th of that turns out to be a nice integer like 20 degrees. But if we started with 100 degrees in a circle, 1/18th of that would not be a nice integer. So one benefit of defining degrees to be that there are 360 of them in a circle makes it so talking about some random fraction of a circle still gives you easy to deal with angle measures, usually integers. Radians are totally different. So usually when you're talking about radians, you're not necessarily talking about an integer number of radians, but radians are interesting and important and useful regardless. Why is that the case? What is 1 radian, first of all? Before we even talk about why 1 radian is important, what is 1 radian? Well, the way you convert from radians to degrees is you multiply by the conversion factor of 180 degrees is equal to pi radians. But if we want the units to cancel out, we want to put radians in the denominator because we have 1 radians out here. So we want this to be pi radians over 180 degrees. If we were going from degrees to radians, we would multiply by the reciprocal of this, so that way the degrees would cancel instead. But since we're going from radians to degrees, this is about 180 over pi degrees. And if you put that in a calculator, it's about 57 degrees. So 57 degrees is nothing special intrinsically, but 1 radian is still very special, because if you move 1 radian along any circle, it doesn't even have to be the unit circle. If the radius of the circle is r, and you rotate 1 radian, the amount of arc length that you have moved along the circle is equal to the radius of the circle. Now that's a very special fact. So that means 1 radian is equal to 1 radius of arc length. That's why it's called a radian, because it's basically measuring how many radiuses you're moving in terms of arc length. And so if 1 radian is equal to 1 radius of arc length, then just to convince yourself that that's true, you can think about what that would mean about 2 pi radians. So 2 pi radians should be a full circle. And so if 1 radian is corresponding to 1 radius of arc length, 2 pi radians is corresponding to 2 pi radiuses of arc length. And as we know from geometry, 2 pi r is literally the circumference of a circle. So 2 pi radians corresponds to 1 full circumference of arc length. So it must be the case that 1 radian is indeed 1 radius of arc length. So this is what makes radians interesting. And depending on what we need to do, we're going to choose degrees or radians to make our life easier. With that being said, let's do one example of converting from degrees to radians, just so you know how it's done. So if we're starting at 20 degrees, we would multiply that by the same conversion factor, but the reciprocal of it to make sure the degrees cancel. So we would say 180 degrees, and this would be pi radians. And that would equal 2 pi over 18, so pi over 9 radians. So 20 degrees is equal to pi over 9 radians. With that being said, we have all the tools necessary to build a new version of trigonometry. So I'll see you in the next lesson to do that.